So there's a setup that I have. So we know that when we were looking at choosing our u, if I think about Liate, one of our factors we have is algebraic. That is the x cubed one. One of them is exponential. That's e to the 3x. Algebraic is the one that we want to be our u. Also, excuse me, that makes sense when you're using the table method, because if you keep differentiating x cubed, that's going to eventually become 0. So I have x cubed, 3x squared, 6x, 6, and then 0. Stopping once you reach 0, because that's how many rows your table is going to have. And then for dv, you want to keep integrating it for the number of rows you had for the u column. Do want to make sure, remember u substitution, where u would be 3x, so u prime is 3. So since this is an exponential, like that's not going to change each time we integrate. So we're basically going to be multiplying by 1/3 every time we integrate going down the rows. And then to form your answers, remember we have the diagonals. So bam, 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 bam. 4 diagonals, and then the pattern is always going to kind of stay the same. Always start with like keep the same sign, and then you switch the sign, keep, switch, and if there's more diagonals, you just kind of keep repeating that. Keep, switch, keep, switch, keep, switch. Where that is coming from is when we do have the actual rule for integration by parts. We have like that uv minus an integral, where like that first term is the same sign, and then that negative is coming from where we switch. So like the table method is just us repeating integration by parts over and over again. So for my final answer, kind of writing out this antiderivative, I have multiplying down, so I have keep, switch the sign, keep the same sign, and we're thankful we have the table method, because this would be a pretty obnoxious problem to do using the long way, and I'm writing too large. Switch the sign, and then of course don't forget your plus c. If you're doing this one the long way, with like the repeated actual integration by parts with like the formula and all that, you would end up doing integration by parts 3 times. So definitely the table method allows us to do things a little bit more efficiently. But do want to emphasize the table method only works if that u's derivative is going to eventually become 0. Questions on that problem at all? All right. So now for the weird examples, I just have kind of 2 slides. The first one will have 2 examples on it, and then that last one will be like the really long one. So one unique thing about integration by parts is it can actually be used when you have a single term in the integrand, where we don't clearly see that we have a specific product. So like looking at this problem, I do want to make sure we don't mess up and not think of something correctly. So like when I look at this problem, this is the integral of the natural log of x dx. Don't be confused. We don't know the integral of the natural log of x. Like we know the derivative of the natural log of x. We know the derivative of the natural log of x is 1 over x. We do know that the integral of 1 over x is the natural log of the absolute value of x plus c, but we don't have a rule for integrating the natural log of x. Likewise, next to it, that other problem, the integral of arctangent, we don't have a rule to integrate arctangent. We have an integral that is equal to arctangent as an antiderivative, but we can't integrate arctangent itself. So whenever we have a function that we don't know how to integrate, we actually are going to use integration by parts. And the way that we would split it up and use integration by parts, still the same way, we're going to have to identify our u and our dv. Not going to be able to use that quick table method because none of those are going to have a derivative that quickly goes to 0. We're going to pick our u to actually be the function that we don't know the integral of. And your dv is actually just going to be the dx. Some people like thinking about it as, well, this is really the natural log of x times 1, so there technically is a product there, so my dv is going to be 1 dx. So then what we did yesterday, we had to take the derivative for du, integrate to find v. The derivative of the natural log of x is 1 over x, that's du over dx, so I'm just going to move the dx over to the other side. The integral of dv is just v. The integral of dx, the integral of 1 dx is going to give us x. Using the formula, I'm going to have u times v minus the integral of v times du. So setting this up, u times v minus the integral of v times du. Definitely can simplify this before integrating that integral, bringing down that first term, x times the natural log of x minus, well, the x times 1 over x is just 1. What's the integral of 1? Just x, and then don't forget your plus c. Some textbooks actually treat this as a rule, and I know even some calculus teachers make sense memorize that like the natural log of x is x times the natural log of x minus x plus c. But honestly, I don't think there's a reason to memorize it because it is just as easy to derive using the integration by parts formula. Question on how I did that single-termed integrand. All right, go ahead and try that second one on your own then for me. We don't have a rule on how to integrate arctangent, but we can figure out how to integrate it by treating it as kind of like arctangent times 1. So go ahead and integrate that one for me. And then we actually just have one more example to do after that one. I'm going to give you a few minutes to try it on your own first. So looking at this one, we're going to let u be the arctangent of x. dv is going to be dx, or 1 dx if you want to think about it that way. Take the derivative of arctangent to find du, integrate dx to find the v. Using the formula, again, I couldn't use the table method because the derivative of u was never going to reach 0. And we have u times v, so x times the arctangent of x, minus the integral of x times 1 over 1 plus x squared. This is a quotient. Again, we can't forget everything that we did first semester. Looking at this one, the difference of the degrees is just 1. So this is going to be a natural log derivative where u would be equal to 1 plus x squared. So of course, u prime is equal to 2x. Pretty easy to see now. The x would cancel out. So we would have a coefficient of 1/2 in front. And then this will be the natural log of the absolute value of the denominator plus c. So the integral of arctangent of x is that whole statement. Technically, those absolute values in the natural log could be parentheses because 1 plus x squared is always positive, but you can also just leave the absolute value there. Questions on either of those two questions? All right, last one. I did save this one for last for a reason. I don't really have like a name for it, but it's kind of just like a weird thing that can happen when you're integrating by parts. So let's talk about why this is going to end up being weird. First off, looking at this one, like we can't integrate this any other way. There's not like a smart u and u prime to cancel out. And when we're looking at it, we recognize that there is a product. So it is probably going to be integration by parts. And the issue of what makes this one weird is when we're looking at to choose what we want to be our u to v and what's going to end up being the dv. We have an e to the 2x in here, and then we also have a cosine of x. Well, e to the 2x is the exponential. Cosine of x is the trig. And the issue with this is kind of, those are like the two least ideal options we can have for our u. Reasons why they're least ideal. We know that if we keep taking the derivative of a trig, you're just going to end up with another trig. Same thing if you just keep integrating it, it's still going to be trig. Likewise, that same thing is true for the exponential. As you keep taking the derivative or integral of an exponential, it's literally just the same thing over and over again. So we're never going to end up with something simpler. So some weird things happen when we start approaching this problem. Again, I do want to make sure it's clear we can't do the nice, convenient table method because neither the derivative of a trig or the exponential will ever reach 0. So I'm going to go ahead and let the best case I have, the trig is going to be my u. So I'm going to have the cosine of x here. dv, that's going to be e to the 2x dx. And I want to just kind of do it as I know how to do it. What is du going to be? The derivative of cosine is negative sine. Integrating e to the 2x, don't forget your u substitution. U is 2x, u prime is 2, so we're going to have 1/2 e to the 2x left over. Then we're going to go ahead and do u times v minus the integral of v times du. Filling this in to kind of see what we have so far, I have 1/2 e to the 2x cosine of x minus the integral of 1/2 e to the 2x minus sine of x dx. Do notice I did kind of go ahead and move that negative on the outside in the 1/2. You don't have to do it that way, but I just like kind of getting sometimes my coefficient and any extra negatives on the outside. So we're left with this so far. We're not done. We're not done until we get rid of all of the integral signs. Looking at the integral we have left over, what's kind of the issue we notice with that integral that we have?
It's gonna, when you integrate it or when you do integration by parts, it's gonna keep repeating.
It's going to keep repeating. Like we already know kind of where this is headed. Like if we keep taking the derivative of trig, like you're still going to have trig. If we keep integrating exponential, like we're going to keep ending up basically with like that e to the 2x is almost never going to go away. Like it's always going to be there. And then like sine and cosine just are going to keep switching back and forth. We don't know what else to do though. Like we do know this is integration by parts. So let's just go ahead and why not? Let's try integration by parts one more time. Still going to let the trig be my u. So du in this case would be the cosine of x. My dv is e to the 2x dx. Integrating this, we still end up with this 1/2 e to the 2x. Do want to be careful as I kind of write my answer, especially with that 1/2 there. Get this to scroll a little bit. So kind of pulling things down and seeing what I have so far. So I have 1/2 e to the 2x cosine of x. This pen has not been working all day. Try that again. So 1/2 e to the 2x cosine of x. One of these days is going to write. This plus 1/2 is going to have to come down. And I'm going to be careful because I'm doing integration by parts on this integral. So I am going to kind of put it in brackets. So then doing my integration by parts formula, u times v minus the integral of v times du. I'm going to go ahead and move that 1/2 on the outside. Again, you could have left it on the inside, but then I have e to the 2x cosine of x dx. So that was my second time of doing integration by parts. What do we notice about that integral left over?
It's the same thing.
It's the same thing. I'm glad you noticed that. So again, like you're still going to have to do integration by parts. Like you still have an exponential times this trig. But we can kind of see, as I think it was Seth who mentioned earlier, like this is just going to repeat. Like we're going to be in this endless loop of just always having a trig times an exponential. So like the big idea that we're looking at is this is what we're trying to get to evaluate. We need to find the antiderivative of that. Well, now like the antiderivative of that includes the original answer right here. So instead of just continually doing integration by parts, which to be honest would last literally forever, we can kind of set up an equation. And the equation that we're going to basically set up is, hey, this is the antiderivative. It's not the final answer because it still has an integral sign in it. But all of this is equal to what we started with at the very beginning. And if we think kind of mathematically, that is an unknown in itself. Like in math, something that's unknown, we can treat it like a variable. So we can literally treat this entire integral as its own variable. So like if I want to solve for it, well, let's just get all of that same variable to the other side of the equation. So we are literally going to have to add this term to the other side. And I'm going to rewrite it real quickly just to kind of distribute that 1/2 across. We do still want to make sure we're doing proper algebra. So right now my entire antiderivative looks something like this. 1/4 e to the 2x sine of x minus 1/4 integral of e to the 2x cosine of x dx. And this is equal to 1 integral of e to the 2x cosine of x dx. I put that 1 there just to kind of think about, like, it's like we're saying 1x. So what do I need to do to both sides? I basically need to add 1/4 of that integral to both sides, and then basically solve for that integral. And why am I solving for that integral? I'm solving for this integral because that's basically the original thing that I was trying to solve for. So solving for it, and again, this problem's not a short one as I keep scrolling. I have 1/2 e to the 2x cosine of x plus 1/4 e to the 2x sine of x. I added this integral to the other side. 1 plus 1/4 is 5/4 of the integral that we're trying to find. Since I'm trying to solve for that original integral, what do I need to multiply both sides of this by? 4/5. And so basically what we're going to get is this original integral that we were trying to solve for is equal to 4/5 of 1/2 e to the 2x cosine of x plus 1/4 e to the 2x sine of x plus c. Not a short problem. I think it definitely takes like seeing it one time to kind of see how it works. I'm going to try to zoom in to show all of it on the same page. So yeah, it's going to be a little bit small. Again, this is only going to show up when you end up with like those last two things of Liate. Like it's only going to really happen when you have a trig and an exponential mixed together, because pretty much for all the other ones, like you'll eventually have something that's doable for the most part. And again, the reason why we could do this is the original integral we were trying to solve showed up inside the problem itself. So we kind of just turned it into an equation and solved for that original integral we were trying to find. Questions on that big old problem?
So is that the answer?
That would be the answer, yes. Like you could distribute the 4/5 across, but this is the antiderivative of that original integral.
Mhm.
And you could always check it, and like kind of how integration by parts, like I haven't checked any of our answers because it's kind of like usually a really gross derivative defined. But basically what's happening is like when you find the derivative of this, it's like you have the product rule twice, and we know that some of the derivative's cosine becomes negative, so end up like you find the derivative and then like equivalent terms cancel out. And that's why we kind of have like this ugly antiderivative and a simpler integrand. But yes, this would be your final answer, or you could distribute the 4/5 across. Any other questions? All right, so that's where I'm going to stop the notes for today. Your assignment is still the same assignment from yesterday. Homework number 1, integration by parts. Again, not all of those deal with integration by parts. I kind of let them mix together to force you to remember all of your integration methods that we have learned. Tomorrow, we are going to talk about improper integrals, which is another BC only topic. And then basically we're going to end up a week from today is going to be your first quiz over these integration methods and the second fundamental theorem of calculus, which is going to be different, but in many ways related to the first fundamental theorem of calculus. So with that being said, like if you are good to go and don't have any questions, feel free to go ahead and log out and get ready for 6th period. If you do have any questions, definitely hang back. Class isn't officially over until 1:10. And then of course, if you do need more help,